So if you go to TinkerCAD.com and sign up for an account, you can join now with any number of sign-up options, a specific email or Gmail or an Xbox account or a Facebook account. I already have a personal account that I initially set up when I was looking for easy design software for my 3D printer. Originally, TinkerCAD was just 3D design software. It didn't have anything electronic whatsoever. So if you needed to quickly do something simple, like, for example, making a block and putting a couple of holes in it, and maybe putting a cone on top. You could extremely quickly, with very little time spent learning the interface, create 3D designs. And then once you were ready to print them, click export, send it out as an object file or an STL file or GLTF file or an SVG if you want to do some laser cutting. And if you haven't done much mechanical design or 3D design, maybe you're coming from a computer programming course or an electronics course and you haven't done much mechanically, this is actually a pretty fun place to start. That's as much as I'm going to show you for now. What we're interested in is circuits. So from circuits, you can quickly create a new circuit, and it starts off with your standard blank canvas, and on the right, a library of components that you can drop into that blank canvas and connect together. So we're just going to recreate what we did in hardware by grabbing an Arduino and grabbing a breadboard and zooming to make everything fit. We're going to grab a resistor and right click on the resistor, bring up the resistor, and it is a 10K resistor. You can choose the units here. You can also name it here if you wanted to, but it's not really necessary. We're going to grab an LED. The long leg is the anode, which is the positive leg, so we want that to be connected to the Arduino. You can choose what color. We can also call this LED 1 or floor 4. It doesn't really matter. We're going to connect the resistor to pin 12, which is going to be our digital output. And if you move things around after you've dropped it on the workspace, you know, the wires and connections will just stretch with you. We're going to grab a push button, and that push button is going to be connected to input 11. The other side of the push button is going to be connected to the positive rail. And the cathode of the LED will be connected to the negative rail. We'll grab the 5 volts from the Arduino and connect it to the nearby positive rail. We'll grab the ground pin and connect it to the negative rail. And I want that actually to move over one, so we can just drag and drop the connection point. And then a jumper from the negative rail to the opposite negative rail, which completes the circuit for the LED. And that's it. We have a fully functioning circuit in the simulator for an Arduino, just waiting for code. When you select code, the first thing that's going to come up is the default option, which is code blocks. It's very simple, drag and drop, similar to Scratch. if you have an experience with that. But we are going to program this not in drag and drop blocks, but a text editor in the C++ variant that Arduino is programmed by. And let's just zoom to fit again to get this out of the way. Before we go on, you can also color code things. So just like with the original physical circuit, I can color code the positive wire to be red, the negative wire to be black. Just to keep things organized in our brains. So now anything that's connected directly to the positive supply is red, and anything connected to the negative supply directly is black, and we're using different colors for everything else. By default, every Arduino that you purchase will come with a program running on it that blinks the LED on board that's connected to pin 13. We can easily test the simulator just by running this program by clicking on Start Simulation. And looking at the simulator, we can see that the onboard LED that's connected to pin 13 is in fact blinking on and off once a second. We're going to stop the simulation here and erase the default program and build things up from scratch. And I'm going to change the default random 2-word name of the project to something that makes sense, more sense than Frantic Jacob. So we just click Intro to Arduino, PB and LED. You'll notice all changes are saved here. Anytime you make a change to your program, anytime you make a change to the wiring, it will very quickly update the saved project, and as long as all changes are saved is seen here, you are free to close your browser or just go back to the project space and move on to other things. Just like in any other program, where if you're working on an Excel sheet or a document and you want to save a revision, the easiest way to do that is just to duplicate what you've done when you're happy with it, which will make a copy of the program, well, a copy of the project, and open the copy of the project in a new window. All changes are saved. We can go back. If we open our project, we want to tinker it, and we want to add some first code. Before we start adding code, there's a little tiny bit of what the heck is this? So what the heck is this? This is the default code that you will always be staring at whenever you start an empty Arduino program. In short, any code that you put in this function called setup will be executed once at the beginning of runtime. So when you first apply power, when you first download the program, or if you click the red reset button on the board, it will stop everything, do some cleanup, and run the code that's in setup. But only once. Once the setup code has been executed, then execution passes to the function called loop. And it stays there, cycling over and over and over again as fast as possible until you cycle power or give it a new program or press the reset button again. As a rule, when a person is initially learning how to program, there is a hello world example to follow. If you're programming on a computer, normally that takes the form of actually printing the words hello world, but we're going to do something a little bit more hardware specific. Since it's an Arduino, our version of the hello world program is blinking an LED. Because that's the whole point of the Arduino, is to be able to control something based on inputs and code and decision making that happens in the program. So we're going to start off by doing nothing more exciting than turning on the LED and leaving it on. We can do that since it's not something that necessarily needs to happen over and over and over again. We can do that right in setup. Now the first step, as you may recall, is to tell the Arduino that one of these I/O pins is being used as an output to enable the internal transistors that will connect that pin to 5 volts or 0 volts under our program's control. We do that with a function called pin mode with a capital M. Open some brackets, and we tell it what pin we're referring to. In the case of our program, our pin is 12. 12 controls the LED. So we're going to change the mode of pin 12 to be an output. Close the bracket and add a semicolon to the end of your instruction. Now this all by itself is a valid program because we have configured a pin to be an output instead of an input. If we send this out to the Arduino right now, it will do something. We just won't see what it does. Because initially when you change the mode of a pin to an output, it starts off low. It starts off with the NPN transistor connecting it to ground. So our LED will not actually turn on. The next step is turning on the LED. And we do that by telling the Arduino that we want to turn off the transistor that's connecting the pin to ground and turn on the transistor that connects the pin to 5 volts, which will then supply the LED. We do that with the function digital write because we are writing a value to a digital pin. Digital write, capital W. What pin are we changing the state of? 12. The pin is already low because it's connected to ground. The opposite is connecting it to 5 volts, which is high, in all capitals again. This by itself is also a valid program and actually does something. So if you watch the blue LED while I click simulate, this program configures the pin 12 as an output and connects pin 12 to the high side, which is 5 volts. So let's stop the simulation, turn on the LED for 1 second before turning it off again. Delay 1000 milliseconds, add a semicolon to the end of your command, and write to the digital pin a logic low. Watch the LED, simulate, LED turns on, waits 1 second, turns off. And because this code is in setup, which only runs each command once, it turns it on, waits 1 second, turns it off, and then sits there doing nothing forever. We're almost there, because what we want is for the LED to flash. So in order to make the LED flash, we need an on time and an off time, and we need it to loop and do it again and again and again. The easiest way to do that is to leave the configuration of the pin in setup and paste turning on and delaying 1 second and turning off and delaying 1 more second before turning it on again into the loop function. Poof. Simple as that. Now, because this is a computer program, and because the classic Hello World program prints something to the computer screen, we're going to add that functionality right now, because later on it's going to be very handy for diagnostics and status updates and just to make your elevator program much nicer to look at. Stop the simulation, and just like configuring pin 12 to be an output, we are going to initialize the serial communications between the Arduino and the computer in setup. It only needs to happen once. Capital S, serial, is the library name. A library is a collection of functions. The serial library has a function called begin. And when you begin, which is initializing serial communications, you also have to tell it what the port speed is. Many devices will come configured at 9600 baud, 9600 bits per second. I typically go faster than that, not super fast, but fast enough to do everything that I need to do at 115,200 bits per second. So at the same time that we turn the LED on, we can print a message to the user. Serial library dot print, open bracket, and what do we want to print? LED on. And then after 1 second, when we're turning off the LED, LED off. Simulate. Now at the moment it doesn't look any different because you haven't seen the serial monitor yet. At the bottom of your screen, over on the right side, if you click the serial monitor, you will now see the output of this program. In the serial library, the print command prints whatever's in the brackets and then sits on the same line and waits for the next thing to come. We don't really want it to stay on the same line. We want a new line after each print. So we want LED on and go down to the next line, LED off and go down to the next line. We do that by using print ln for print line. We can also keep track of things. For example, we can keep track of the number of times it's gone through this loop. So let's declare a variable, a little container that can hold the number. So we're going to make an integer which takes up 16 bits of the Arduino's memory. Int. We name the variable. I'm going to call it loop count. And although we don't have to do this, it's generally good practice to initialize the variable to a value that makes sense. So our integer, called loop count, is initially going to be equal to 0. Semicolon. At the end of loop, we're going to print the number of times it has gone through the loop. And by the time it's gotten to serial.println loop count, it has in fact gone through the loop once. So let's increment loop count by 1 before we print it. Now let's put all of these print statements on one line for each loop through the program. So I'm going to want to go into the loop and print LED on, but not go to the next line immediately. So we're just going to use print. I'm going to add a dash to that print because I know that something's going to come after. What's going to come after is LED off, and I just don't want the L for the LED off to be right after the ON. After printing LED on in the dash and turning on the LED and waiting 1 second, I want it to print LED off on the same line. And I also don't want this to automatically go to the next line because I want the number to follow. And I'm going to add another spacer to that. But then after loop count, the number has been printed, I do actually want to do a carriage return and go to the next line for the next time through the loop. So I will keep the print line for that last print statement. If we run it, we see what's different. And before we wrap up this section, I'm going to just clean up this program a little bit and make it easier to read. And we're going to do that in two ways. One, we can add a comment to our program by adding 2 slashes at the beginning of the line. This makes the compiler ignore whatever comes after it. This is entirely just text that is not run on the Arduino. It never even makes it to the Arduino. It doesn't take up any space in the Arduino's memory. It is entirely for you, the programmer, and for programmers that come after you to understand what the program does. So I'm just arbitrarily going to say that this is a program to flash an LED and print the number of flashes. At the end of this line, this variable, we can tell ourselves, remind ourselves, or tell other people what loop count actually is. Although it's pretty self-explanatory, when you look through the program, you can, declare an integer to count number of flashes. LED on pin 11. 12. Wait X milliseconds. And you can embellish this any way you see fit. Start this. Make sure that there's no mistakes. There are no mistakes. All changes are saved. Go back to a project space. And again, if you wanted to save this and build up from it, you could duplicate it, or you can just simply keep it there and come back to it later. All right, so we've done a few things that are interesting, but not terribly useful. Let's get going with something a little more useful and heading towards a positioning application like an elevator. Since a push button state is just on or off, it's a logic variable. It's never going to be 2 or 3 or 10. We can use a Boolean variable type. We can call this push button state. We can initialize it, but we don't really need to, since before using the push button state, we are going to be checking the push button state. We're going to assign the variable push button state whatever is returned by the function digital read, capital R. And since we're not writing a state, we're reading a state, we don't need 2 parameters to be passed to this function. We only need to tell it what pin we're asking the function to look at and report back to us. So in this case, it's pin 11. Step 2. If push button is pressed, add 1 to position. So now we're making decisions, and we're getting into what are called conditionals. The most basic conditional that you're going to run into is the if, then, else statement. If this is true, then do this. If it's not true, you can check for another condition or a third condition or a fourth condition. And then finally, if all else fails, else, do this. We're going to keep this simple, and we're going to keep it all isolated in this so that it's extremely clear and extremely easy to read. But later on, when we're doing the full elevator workup, I'll introduce you to some shortcuts. For now, if, and in brackets, we put the condition the decision is being made upon. So the decision is if the push button is pressed. If the push button is pressed, we're expecting PB state to come back as true, or 1, or high. Those are all three valid options. But we're going to start off with high, because when we're controlling the digital output, we use high and we use low. So when we're reading the input, we're also going to use high and low initially to keep everything very clear. If push button is pressed, then we expect PB state to return a high. If PB state equals high, then do something. So, two new things. In C, a single equals is an assignment. In this command, we are assigning the value of digital read pin 11 to PB state. In the initial creation of this variable, we are assigning the variable position a value of 0. So in this code right now, if we were to run it, PB state is initially assigned the value of pin 11, high or low. If I left this exactly as it is right now, then high would be assigned to PB state. It would overwrite PB state. And regardless of whether the push button was actually pushed or not, when it got to this deciding point, high would be assigned to PB state, and because it was high or true or 1, it would execute the code, which means it would execute the code all the time. In C, to compare two values, you use a double equals. That's going to trip you up a lot until you get used to it. It's very frustrating, and even after years and years and years of programming, you will, just being human, make this mistake. Now, if this is true, it's going to execute the command that follows. In this case, we're only doing one thing. We are incrementing position by 1. And we could just simply leave it at that. But if you were checking the state of the push button and you wanted multiple commands to be executed if push button is high, then the way to do that is not with multiple if statements with a single command. It would be to add curly braces. These curly braces can hold any number of additional instructions. So we could increment the position, we could check the value to make sure that it isn't getting too high, we could automatically print out the value, but only if the push button was high, just by using the curly braces to contain all of the different things that we want to do if the push button is pressed. We don't have to in this case, but for the moment, again, just to keep everything standard and clear and flexible for when we inevitably have to make changes, I'm going to put everything in curly braces as if it's multiple commands. Step 3. If push button is not pressed, subtract 1 from position. I'm going to be lazy or efficient, depending on how you want to look at it, and copy this text, paste it down here, and just change what's relevant. So if the push button state is low, I want to subtract 1. Next up, let's print the position to the serial console. Using print line so that each number comes up on its own line. If position is greater than or equal to the top floor, now we turn on the LED. At this point, there's two things that we need to do. One, how do we define top floor? Are we going to make the top floor the floor number, the floor 4? Are we going to be a little more fine-grained and measure the position. Say the top floor is 40 feet above ground level. This is not too important right now, but it will be important later, because later on, when I do my elevator, I don't simply want the floor to magically change from 3 to 4 1.5 seconds later. I want to do some limited simulation of a physical reality. So mine is probably going to be something like a floating point number, where I can be at floor 1.0, 1.1, 1.2, 1.9, and then arrive at floor 2. Or I may decide to use the height above the ground, measured in feet, measured in meters. I'm not really sure right now. But for the moment, we're going to consider the top floor to be floor 4, so it'll be an integer. We'll just use whole numbers and delays to simplify this for now. We still need to define what the top floor is. So up here, where we are declaring our variables, although the top floor is not needing to be a variable, because my program is obviously not going to, in real time, change what is considered the top floor. It's really going to be a constant. I am, for this, still going to maintain some consistency and make the top floor be an integer. And the top floor is going to be equal to 4. And while we're at it, let's also define at least one other position, which is going to be lobby. And that's going to be equal to 1. So now we can go down and make the comparison. If position is equal to top floor, then do what's inside the curly braces. What we're going to do in the curly braces is turn on the LED. The LED is connected to pin 12, and we're setting it high. Now, since the next pseudocode is, when we're at the top floor, also print floor 4, we can actually combine these two steps. Serial library, print with a line feed after it, floor 4. On the other hand, if we're at the ground floor, which we are now going to call lobby, we'll again just copy this code, paste it here, and change what's appropriate. So if the position is now equal to lobby, we're going to turn off the LED and print. Oh, just realized I missed the quote for floor 4. For now, I'm going to complete this program and I'm going to get rid of this code, except for the delay. But because I don't want the delay to be there right now, I don't want the delay to be executed, I'm going to put 2 slashes in front of it, which comments it out, and it becomes text that the Arduino will ignore. So at the moment, within the loop, there are no actual delays. So we'll start the simulation and we'll see what happens. and immediately the LED is on, which all by itself is curious because the LED shouldn't be on until it's at floor 4, and if we're starting from floor 0 and we're not pushing the push button, why is the LED already on? Well, let's take a look at the serial console and see what's actually happening. 1800. That's an awful lot more than 4. So the number one thing that we know is that it's counting up and it's not stopping at 4. The number two thing that we know is that it's counting up even though we haven't pushed the push button, which is the condition for counting up. So let's stop the simulation and briefly start and stop the simulation. So in the time that it took me to start and stop the simulation, it did count up to 15. And if we scroll back through the output of this program, we can see that it was at some point at the lobby, because the lobby is floor 1, and then it was at floor 2, floor 3, floor 4, printed floor 4, and continued flying past floor 4 to be 5, 6, 7, 8, 16,000. So if you go down to the little squiggle trace here and click that, then you will get an active plot of the numbers that are coming out to the serial monitor. If I push the button, the numbers start going up. If I release the button, the numbers start going down. Now, this PreLab video that you've been watching has been a very cut down version of a full tutorial that you will eventually see near the end of the course. At the moment, I'm going to stop developing this program and instead leave you with what we've done so far. This very, very quick start into one indicator and one push button and the basic structure of a program, and using TinkerCAD to do the program, simulate it, be able to see variables, be able to see output that will help you to see what your program is doing and not guess so much. And I'm going to change gears and give you some resources that you can look into to learn more. So the first resource, obviously, for an Arduino, Arduino.cc is everything Arduino. Anything you want to know, including downloading the software and going through additional tutorials, or if you just simply have a question about a specific command, or you're looking for a specific command, you can come to the reference and you can read up on digital read, what everything means, get example code to run. What the details of pin mode are, and how to use it in your program. Descriptions of the digital pins on the Arduino, and a little bit of history. Specifically, what input pull up means and does would be high on my list of what you should check out first. In addition, you're going to want some structure in your program. So by structure, I'm talking about what loop does, what setup does, how to use a for loop. This will be important for your programs. Various Boolean operators for your or and not and. Some shortcuts. For example, if you want to increment a variable by 1, you can actually do that variable plus plus instead of writing out variable equals variable plus 1. When we're reading the push button, because it is connected to ground and the state is opposite of what was expected, you're going to be using the logical not operator. Various math components, including constrain, which I use a lot. It's extremely handy for making sure that values don't run away on you. Delays in milliseconds, delays in microseconds, keeping time relative to when power was applied, how to use the serial communications, and what pins are available on different boards. It's all here. You can also find information on libraries. Not just the library that comes built into it that we've been using to do programming already, but many, many, many libraries that are developed to do amazing things. Now, additionally, if you do have an actual physical Arduino, there are two ways you can program your Arduino. One is by going to downloads and downloading the actual application that is installed on your computer. This is my preferred IDE for the Arduino. I have run into a few problems where the cloud-based Arduino IDE, the libraries are a little bit different and don't always work as I expect. And in some cases, the libraries that I want to use don't even exist. However, if you do go to Arduino Create, their online IDE, you don't have to install anything. You can go straight to the web editor. And although the layout of this is different, it is very familiar. The main thing that is really handy about this is that, unlike the simulator in TinkerCAD, all of the libraries available and all of the examples from those libraries are also available in an easy-to-use search bar. You can go to the basic examples and learn how to blink an LED. They happen to be using LED built-in, which is a constant that becomes pin 13, using the digital pins, reading a button. All of this code is copy and pasteable into TinkerCAD. The reason we've been using TinkerCAD instead of this editor, however, is because this editor does not do simulation. This is an editor for being able to download a program to an actual physical Arduino that's connected by USB. TinkerCAD, on the other hand, actually simulates an Arduino, so you don't need hardware. Go and explore these resources and apply them to the elevator project. But don't get hung up on the elevator project. Do some playing. Don't get hung up on overly complicated examples that you will find on the internet. Most of them are just showing off. Stick with the basics, stick with the fundamentals. Make sure it makes sense to you. Make sure it makes sense to your group. Good luck and have fun.